Jesus.
You might not want to do it now.
Is it on? Oh. Hi. Sorry, my computer froze. Um, hello and welcome to All About Numbers. You guys have just got done watching the CS50 video on binary numbers, and this follows right afterwards. So you'll definitely need that. I'm also including a reference to this Java document, Primitive Data Types. This contains a great summary of all the different data types that there really are. We're actually only going to focus on a couple of them because you don't really ever need byte or short. But we are going to focus on these middle four: int, long, float, and double. Of course, you already know what Boolean is, and char we'll get to, but it's basically a string. But let's go ahead and focus on those. So I've done some initial setup for your project this unit, which is to create a payroll program. I've got a little controller here, and I've also got a model over here. So there's that. And the model doesn't actually do anything yet. The program itself actually doesn't do anything yet, but that's okay. Because the only purpose that I have set this up for is to play with some numbers. So there's four data types that you really need to know. You need to know about int. You need to know about double. You need to know about float. And you need to know about long. Not ling, long. Okay, so let's start with the smallest one, which is an int. So an int stands for an integer, but it's not the only number of integer type. Short is a type of integer, int is a type of integer, and actually long is also a type of integer. The int data type actually just specifies the most basic type of integer you can get. Ints run anywhere from 2 to the 32nd to 2 to the negative 32nd power. So it gives you a pretty significant portion of data. And actually, I think that's 2 to the 16th, not 32nd, but whatever, that's not important. The important thing is, if you're only looking to work with integers, you want to make sure that int is the number that you're choosing, as long as those integers are small. Okay, the reason why is because it has to do with what you learned last time in terms of how binary numbers are written with bits. Okay, so last time you should have learned that in binary, let's just say you wanted to represent the number 12 in binary. So go ahead and think about how to do that for a second. Okay, so let's see, we got here is 1, here is 2, here's 3, here's 4. Remember this? Oh, yes. So we get 4, and then if you add another 1, that's the 8ths place. We can't go to 16, but 8 plus 4, that's 12. So this right here, this is actually a 4-bit representation. 1, 2, 3, 4. Okay. So 4 bits, that's really not that much, and the int value actually goes up to 16 bits. So you can go all the way up to 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Let's see if you can figure out what number that is. All right, I'm going to do the math real quick. Here's 1, 2, 4, 8, 16, 32, 64, 128, 256. Oh boy, this is going to get hard really quick. 512, 1024, 2048, 4096, 8,192 maybe? I don't know, it gets pretty high. But the point is you can get up into the thousands basically in binary here. So if you need to deal with integers with 12 bits, which is what each one of these represent, that's what you want to use. Now, why do we care? It's because each one of these bits takes up memory. Now, up until now, you've probably thought of memory as just this imaginary number in your computer that makes it work faster, but the point is everything that your computer does actually uses a portion of this memory. And numbers, by definition, are really small portions, but the more bits that you need to use to represent numbers, the more memory it requires. 12 bits is obviously less, or excuse me, 16 bits is obviously less than double that, which would be 32 bits. This doesn't really matter if you're only working with like one number. So if you have a data model that only needs to work with one number, it doesn't matter at all. However, if you're writing a program like, I don't know, a payroll program that needs to handle thousands and thousands of data entries, this really starts to matter if they need to be all on screen at one time. So that's why we're learning about it. Right, so int is the smallest ones of these. Integers are 16-bit representations of integer-only values. They're not precise, which means that the number 1, you'll never know if it's 1.2, 1.3, 1.4, or 0.9, 0.8, 0.7. You'll never know that in an int representation. Right? So that's int. Next one that's relevant is the long value. So if you change to declare a long, you change int to long, and you actually put an L at the end. Okay? That L tells the compiler that this is a long value number, and it converts its data type into long in the program. Now, long values can hold up to 32 bits, so basically double the length of this. I think you can go up to, 2 to the 32nd power is what it is, I think. Not 1,000,000% sure, but again, not important. So you could really get all the way up to this number in binary if you wanted with a long. And again, it's got the same drawbacks as integer values. The only difference is that this is now a 32-bit number, or 64-bit or something. Hold on a sec. Let me double check those numbers again. Oh, okay. Int is 32, long is 64. So here's what an int can be, and then a long is going to be double that. Okay, but the point is they have different values of bits. So let's, again, integer is 32-bit and long is 64. And again, all this data is right here for you to see. In the primitive data types reference. Okay, but you can imagine that if you're trying to store arrays of integers, you're not going to use this long value because it takes up double the memory of int. As long as the numbers are small, for example, if we needed to store how much money we owe an employee, assuming they're not going to be making several $100 million in salary, which if you're paying an employee several $100 million from a company, you're probably doing it wrong. Let's pretend they're making normal amounts per day. I don't know, $100. We don't need the long denominator. We can just use int. Okay, because we don't want to use excess memory if we don't have to. Oops, not 100.0. Okay, if we don't have to use excess memory, that's a good thing. Okay, you won't really see the effects of this until you start writing larger programs, but trust me, they really add up. All right, so that takes care of your integer representations. Let's talk next about your decimal representations. So there are two decimal representations. There's double and float. Double or float. Okay. So to do these, you just take off the int declaration, you replace it with double. And double holds up to 2 decimal places, I believe. Let me just, excuse me, float is the first one. So float holds up to 2 decimal places, I believe is the correct point. And to convert a number into a float, you just put an F at the end of it. 100.00F. Okay, again, that's important to make sure that the compiler knows that this is a float value and you should store its decimal places. I think it can hold more than 2. But the point is, it is still a 32-bit representation. So the key here is that those additional decimal places, every significant digit here takes up at least 1 bit. Right? So if you have a very large decimal that you need to store, you need to really be careful. For example, even though 100.00234 blah 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 blah, even though this is still just 100, you know, it's not that large of a number, you have to be cognizant of the number of bits that it takes to represent this. Okay, and it's very large. This is actually far larger than a float can handle because you can see the number of decimal places. You know, you can treat each side of the decimal point as its own number that a bit has to represent. So it becomes kind of tricky if you need to handle things with high precision. So when you're doing decimal points, you want to be careful. Floats have 32 bits to represent them. Doubles have 64. You're not going to need anything more than either of those. But the point is, if you need to do you want to use just as much memory as you have to. So if you're handling currency values, let's again pretend that you're paying somebody, and we want to say that we're paying them $100. Okay, we can choose between representing this as a float or a double. We're going to choose float in this case because we don't want to allocate 64 bits to just 5 significant digits because it's unnecessary. Okay, we're going to be wasting a lot of memory, and that's not really a good thing. So we choose float instead of double, and that allows us to store more values. Okay, floats are the ideal choice when you want to store values in a large array, while doubles are the best choice when you need something of high precision. Doubles are very frequently used when you need to do things like 3D graphics. The more complicated your graphics get, the more precise your curves on your shape rendering needs to be, the better off you are using doubles. But again, that requires more processor power, more memory, which of course is your trade-off. But that's how you handle the four different data types. Again, more information is available here. Okay, and allocating these is just pretty simple. You have to remember to include the type of data that you want to include. So if it's int, if it's float, if it's double, and just remember that float and double, or float requires you put the F at the end of it. I don't think double requires anything. No, double, you can keep the float indicator there. And long requires that you put the L at the end of it. It doesn't actually matter whether these are upper or lowercase. I would suggest an uppercase L though, because a lowercase L can kind of look like a 1 sometimes. I don't know why it's not working. Oh, because longs are not decimals, duh. That can happen. So that concludes your tutorial on numbers. Your next task is to complete the assessment on Schoology and then start your project, which is to create a payroll program. And that's it. Hope you enjoyed. Let's see if I can stop.